My numbers are unsorted.
Hey you, are you tired of having unsorted numbers?
Yeah.
Well, I've got just the thing for you. It's called a sorting algorithm. Selection sort is easy to understand and even easier to implement. First, do a linear scan of the entire list and pick out the smallest number. Then, move it all the way to the back. Move the backmost element out of the way, insert the smallest element, and then move the backmost element to where the smallest element originally was. And then mark that spot as sorted and repeat the same steps for the remaining unsorted region. Select, replace, mark, select, replace, mark. Oh, the values are already in their correct positions? That's great, we can just mark them. Select, replace, mark, 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 mark. And take a look at this implementation of selection sort in C. 1, 2, 3, 4 ints. That's only 16 bytes of auxiliary storage. But it's slow, which leads us right into our next one. Now, quicksort is all about partitioning. So how does that work? First, pick a value in the list. I usually pick somewhere around the middle, but this part doesn't really matter. Save it somewhere and let's give it a label. Let's call it pivot, because we're going to use it to pivot our list into two halves. Then take both of your index fingers and place them on both sides of the list. Now move your left finger one space forwards. Is this number strictly less than our pivot element 4? No, it isn't. So we'll stop moving our left finger for now. Now move your right finger one space backwards. Is this number strictly greater than our pivot element 4? Well, yeah, actually it is. Which means we are given the liberty of moving our right finger one more space backwards. Is this element strictly greater than our pivot element 4? No, of course not. Which means we select the numbers at our fingertips and swap their positions. And now we just repeat the steps. Move, compare, right, we can move again. Move, compare, wrong, we stop. Move on the right, we do again, my friend, and this time it's wrong, so now we swap. We keep moving forward until we realize that 4 isn't strictly less than 4, so we should probably stop. And then we keep moving back until both of our fingers touch. And that's when the entire algorithm terminates. As you can see, we've partitioned the list into two halves. One where every number is less than the pivot, and one where every number is greater than the pivot. And quicksort itself is just repeated applications of partitioning. We select a pivot, partition, mark the pivot as sorted. We select two new pivots, partition based on those, mark those pivots as sorted, and so on and so on. I'll leave it as an exercise to the viewer to check if I did those steps in accordance with the rules I laid out or not. If not, be sure to let me know in the comments. Slow sort isn't actually a real sorting algorithm used in practice, but it just blows my mind, so I had to include it. Slow sort is a quote-unquote reluctant algorithm. Algorithms of those kind basically try to solve problems as slowly as they possibly can, but in a non-trivial manner. You know, anyone can just take any old sorting algorithm and add a bunch of steps to waste time. And, you know, that's not what we're looking for, that's trivial. Slow sort, on the other hand, actually needs all of its steps. To grossly oversimplify, basically we do a lot of recursions, and eventually we're left with a list with both halves being sorted. Then we compare the middle and the frontmost element, and if the one in the middle is bigger, then we swap them. And then we basically repeat the entire algorithm again to find the second largest element. Once again, I leave that as an exercise. So there's 52 ways of shuffling a deck of cards, and let's say the way I do it, there's an equal chance for each permutation to appear. So there's a 1 out of 52 factorial chance of, the sorted deck of cards permutation appearing. So that means on average we'll have to do 52 factorial shuffles, and not to mention a linear scan each shuffle to make sure that, it is indeed sorted. So that amounts to approximately, 52 times 52 factorial checks, or approximately 4.19 times 10 to the 69. So yeah, I'm gonna go start shuffling the cards. I'll let you guys know when the deck is sorted.